Hello, my name is David Oakes, Area Manager of Aerothermal Interactions and Signatures at Physical Sciences Incorporated, PSI. Today I'm going to provide you with an overview of the development of a testbed that combines PSI's hypersonic materials testbed technology with a universal testing machine. The result is a benchtop system that enables affordable, in-situ measurements of mechanical strength properties of materials as they are subjected to the extreme environments experienced in hypersonic flight and in propulsion systems. I'd like to begin by introducing PSI. We are a 52-year-old employee-owned technology company that employs more than 250 talented scientists, engineers, and support staff with expertise in high-enthalpy flow technologies and testing, ultra-high temperature composite materials, integrated photonics, and optical sensors and systems for a broad range of applications. We perform applied R&D for industrial customers and all U.S. government agencies, focusing on hardware solutions. Our laboratory and manufacturing facilities are located in 4 sites across northeastern Massachusetts and southern New Hampshire. The hypersonic materials mechanical strength testbed capability we are describing today is located in our 60,000 square foot corporate headquarters in Andover, Massachusetts. Examples of PSI product areas include high enthalpy testbeds, high temperature composite materials, high energy density batteries, custom optical and RF components, laser-based sensors, and radiation sensors. PSI is among the most successful businesses participating in the SBIR program. For every dollar in Phase 2 SBIR investment, PSI has secured nearly 3 times that amount in Phase 3 funding. This SBIR topic recognizes the need for advanced materials capable of surviving the high enthalpy environments experienced in hypersonic flight and in propulsion systems. These extreme environments subject materials to high heating rates that can result in material temperatures exceeding 3,000 Celsius, or 5,400 Fahrenheit, and an impinging flow of reactant dissociated air or combustion products. In addition to the shear stresses that materials experience in high Mach number flows, these materials are exposed to environments with high thermal and chemical stress. There exists very limited fundamental data on the impact of these environments on the mechanical strength properties of materials, critical in their performance for hypersonic and propulsion applications. The Navy challenge addressed in this SBIR topic is the need to develop innovative, affordable thermal-mechanical test methods under a relevant hypersonic operational environment between Mach 5 and 20. The Hypersonic Materials Mechanical Strength, or HMMS testbed developed by PSI in response to this challenge fills a current gap in the DoD test infrastructure by providing an affordable and accessible capability to measure mechanical strength properties under simulated hypersonic flight and propulsion conditions. The transition target for this SBIR technology is therefore low-cost, contamination-free materials testing in flows simulating hypersonic flight and high enthalpy propulsion conditions. Potential customers for this technology are looking for quick turnaround, inexpensive test data needed to qualify existing or new materials or component designs for the high temperature environment experienced in hypersonic and propulsion system applications. These potential customers include government labs in the Navy, Air Force, Army, and NASA, and their associated prime contractors, such as Northrop Grumman, Lockheed Martin, RTX, etc. Any government programs requiring strength testing of materials for high temperature, hypersonic, or propulsion applications are potential customers. Additional potential transition opportunities reside in the $1.56 billion annual commercial market for high temperature materials testing for the aerospace, energy and power, automotive, electronics, and construction industries. ArcJet facilities, such as those located at AEDC in Tullahoma, Tennessee, and NASA Ames in Moffett Field, California, currently are considered the gold standard for high enthalpy flow testing to qualify materials and components for hypersonic systems. The HMMS testbed provides a test environment that is similar to the ArcJet in terms of enthalpy, plenum and test pressure, and flow velocity over test articles with dimensions up to 25 millimeters at a cost that is at least 10 times less than required for testing in megawatt-scale ArcJet facilities. The source of the high enthalpy flow in the PSI testbed is PSI's patented microwave-driven jet or midjet technology. The midjet is a microwave torch that generates high enthalpy flow through expansion of a high pressure plasma formed in an electrodeless discharge in the torch plenum. As a result of utilizing an electrodeless discharge to produce the high enthalpy flow, the midjet produces a clean test environment without any of the copper contamination that results from electrode spallation in ArcJet. By controlling the test enthalpy, determined by the ratio of coupled microwave power and the source gas flow rate, typically air, and the test pressure, the hypersonic materials testbed provides a tunable test environment encompassing Mach numbers ranging from 2 to 17 at simulated altitudes from 15 to 60 kilometers. The HMMS testbed developed in this SBIR program integrates a universal testing machine with PSI's Hypersonic Materials Testbed, or HMT technology. Through its commercial testing services business, PSI utilizes the HMT to measure ablation rates, optical signatures produced by ablation products, and other materials effects resulting from materials exposure to high enthalpy flows at simulated altitudes up to 60 kilometers. The photograph to the right of the HMT photo shows a 1 centimeter diameter test article during exposure to Mach 9 airflow at a simulated altitude equal to 32 kilometers. The image below the photo shows a temperature map of a sample under test measured with PSI's two-color imaging parameter that is provided with the testbed. Exposure times in the HMT typically range from 30 seconds to 30 minutes, depending upon customer requirements. The HMT system consists of the midjet torch with 6 kilowatt microwave subsystem, a pressure-controlled 10-inch diameter flow tube with numerous viewports and 3 options for supporting a range of sample geometries in the flow, and a rack-mounted computer control system that provides push-button operation of the testbed. A photograph of the HMMS testbed with the integrated load frame is provided in the lower right of the chart. PSI has demonstrated tensile strength and modulus measurements of a range of materials heated from 1000 to 3000 Celsius in air, nitrogen, helium, or vitiated combustion flows in the testbed. The image next to the HMMS testbed shows a carbon-carbon composite dog bone heated to 1800 Celsius during recent tensile testing in the testbed. Testbed specifications include an operating enthalpy range between 1 and 14 megajoules per kilogram, simulated Mach numbers up to 17 based on enthalpy and up to 8 based upon the velocity of the jet, heating rates up to 1500 watts per centimeter squared, heated areas up to 25 millimeters in diameter, dependent on the simulated altitude, which ranges from between 15 and 60 kilometers. The current load frame has a maximum tensile load capacity of 50 kilonewtons. PSI is currently 3/4 of the way through a 24-month expanded scope effort under its Phase 2 SBIR contract. The Phase 1 program developed the design of the HMMS prototype system and was completed in July 2020. The Phase 2 base and option programs established the testbed described in this presentation that has been tested to a technology readiness level of 5. The expanded scope effort is integrating a dedicated pumping system with the testbed that will be delivered to NAVAIR in June of 2026. The expanded scope effort is also developing free stream characterization diagnostics to directly measure the enthalpy in the flow and is initiating a CFD modeling capability for the testbed. When fully realized in a follow-on effort, the CFD modeling will provide the capability to tie test conditions directly to hypersonic flight conditions, such as altitude and velocity. PSI has been offering commercial testing services with its underlying HMT technology since 2022 and realized its first testbed sale of the HMT technology in 2024 and presented its first paper reporting high temperature material strength testing data for tactically relevant carbon silicon carbide ceramic matrix composite materials at the 2024 National Space and Missile Materials Symposium held in Madison, Wisconsin. This slide compares attributes of platform technologies utilized for testing materials under conditions representative of hypersonic flight or propulsion environments. PSI's midjet is compared to other platforms based on several key testing parameters related to simulating the conditions at the leading edge of a hypersonic vehicle, including high Mach number flow, relevant heating rates, and the ability to produce relevant leading edge steady state temperatures with an incident flux of oxygen and nitrogen atoms present at the stagnation region that forms at the leading edge under hypersonic flight conditions. The midjet platform stands alone when considering these attributes, along with the additional goals of minimizing both testing cost and test article contamination from the platform technology. The midjet-based platform reduces the cost of testing due to the relatively low cost of the infrastructure needed to operate the facility compared to the hundreds of kilowatts to multi-megawatt inductively coupled plasma torch and arc jet facilities. The 6 kilowatt Hypersonic Materials Testbed provides a clean and accurate test environment at substantially lower cost than these other platforms, with a projected cost of less than $200 per test sample at moderate test volumes. At the completion of the current expanded scope portion of the Phase 2 program in June 2026, PSI will have delivered and demonstrated operation of the HMMS testbed to a NavAir facility, achieving a technology readiness level of 6. As I've described in this presentation, the testbed will be capable of characterizing the performance of materials subjected to simulated hypersonic flight in propulsion environments consisting of high enthalpy air and vitiated flows, respectively, producing test article temperatures in the nominal steady state range of 1,000 to 3,000 Celsius. In addition to measuring tensile strength and modulus, the testbed will be capable of assessing materials ablation rates and induced optical signatures as a function of simulated Mach number and altitude. Together with our transition advocates, Dr. Sung Choi and Mr. Calvin Fawcett, both from NavAir NORCAD, PSI has developed a plan to advance the HMMS testbed technology beyond Phase 2 with additional transition activities. Planned activities include completing the development of a computational fluid dynamics-based process model for the testbed mentioned earlier. A validated CFD modeling tool and process model will provide the capability to directly correlate testbed conditions to specific conditions along a hypersonic flight trajectory. This will enable the design of HMMS tests to meet customers' specific mission objectives. Additional planned activities will extend the measurement capability of the testbed to encompass flexural and compressive strength measurements. An isothermal test capability will be developed by adding laser illumination capability to the testbed to reduce the temperature gradient across the gauge region of dog bones heated on one side with high enthalpy flow. Finally, we plan to scale the HMT technology from 6 kilowatts to 100 kilowatts to extend the test article dimensions heated by the high enthalpy flow up to 10 centimeters diameter. The current lack of low-cost, readily available test infrastructure for developing and validating new materials or material systems and related materials models for hypersonic and advanced propulsion system applications provides the commercialization opportunity for PSI's testbed technologies. To address this opportunity, PSI is pursuing 2 avenues for commercialization. First, PSI offers commercial testing services, where we provide low-cost, high-fidelity testing for customers during the development phase of small-scale components and test articles. The image in the top left of this chart shows an example of a portion of a test matrix executed for a customer recently, in which the ablation rate of 3 materials at 3 enthalpy conditions corresponding to Mach 5, 7, and 9 flight conditions at 32 kilometer simulated altitude was assessed. The data from this quick turnaround testing helps our customers reduce risk and lower cost as they accelerate the development cycle for new materials prior to pursuing ArcJet testing to validate the finalized design. Our current market for testing services is about $250,000 per year and is expected to increase to about $1 million per year by 2030. The second commercial avenue for this technology includes testbed sales to customers with sufficient test volume to justify establishing a dedicated test capability. The total addressable market for testbed sales is approximately $90 million. The planned transition activities after the completion of the Phase 2 program, described on the previous chart, provide opportunities to grow these markets. Expanding the measurement capability to all modes of mechanical strength increases the value of testing to our prospective customers. Scaling up the testbed to 100 kilowatts enables us to test larger test articles and would provide us with the capability to address more of the current ArcJet testing market. This Phase 2 SBIR has developed a high-temperature mechanical strength measurement testbed that can provide the data needed to expand critical material databases used to design hypersonic and propulsion systems that is not otherwise currently available. As I've described, our business model includes providing both commercial testing services at a per-day test cost that is at least a factor of 10 less than ArcJet testing and direct testbed sales. Our preliminary cost analysis indicates that a customer that establishes a test capability based upon the HMMS testbed technology can expect to achieve testing costs per test article that are less than $200 at modest test volumes, which is at least 10 times less than at an ArcJet facility. As we've discussed, our initial transition targets include government labs and prime contractors developing materials and material systems for hypersonic and propulsion systems. Our future development path includes pursuing the post-Phase 2 transition activities I've described in the previous two charts. Finally, we welcome you to reach out to us to discuss your needs for low-cost, high-temperature materials testing to assess ablation rates, material strength, and other materials properties under simulated hypersonic and propulsion conditions. The QR code and link provided on this chart will take you to a page on PSI's website that provides an overview of our materials testing services utilizing the HMT and HMMS testbed technologies. Please feel free to reach out to myself, David Oakes, or my colleague, Dr. Matthew Braunstein, either through our website or the contact information provided here for more information on our capabilities or to discuss your testing requirements. Thank you for taking time out of your busy day to learn about our hypersonic materials mechanical strength testbed capability.